Hi, everybody. Welcome to the weekly colloquium series of the C3.ai Digital Transformation Institute. As many of you probably know, we are a consortium of universities and industries aimed at attracting the world's leading scientists to join in a coordinated and innovative effort to advance the digital transformation of business, government, and society using artificial intelligence, machine learning, and cloud computing. Our institute was started with a generous donation from C3.ai and computing support from Microsoft. The institute is headquartered at the University of California at Berkeley and University of Illinois at Urbana-Champaign. And we have a number of industry, university, and national lab partners. They're listed here. This is the last but one seminar of the spring series. There's one more next week by Louis Shah. We'll talk about COVID-19 medical best practice guidance system. The summer series will kick off on June 10th after a one-week break. And more information about the colloquium series and our other symposia and workshops and everything can be found on our website. And in case you missed any of our previous talks, you're welcome to visit our YouTube website and you can see all our talks recorded there. So before I introduce today's distinguished speaker, I just want to briefly talk about the format. So we're changing the format a little bit for today. So the speaker would like to have questions during the presentation. So if you have any questions, please put them in the Q&A feature and I will read it out to him whenever there's a pause in his talk. And you can upvote a question if you like, and we'll try to answer as many questions as time permits, but we'll ask the ones that are upvoted first. So today's talk is on feedback control perspectives on learning. And the speaker is one of my distinguished colleagues, Jeff Shamma, who's a very well-known control theorist, who's the department head of industrial and enterprise systems engineering here at the University of Illinois. And he also holds the Jerry S. Dobrovolny Chair in ISC. He has been a faculty member at a number of places, most recently at KAUST and before that at Georgia Tech and then at UCLA and so on. He received his PhD in system science and engineering from MIT in 1988. He's a fellow of the IEEE and IFAC. He's a recipient of the IFAC High Impact Paper Award, the prestigious Donald Ekman Award, the NSF Young Investigator Award, and he has been a past distinguished lecturer of the IEEE Control System Society. Jeff currently serves as the editor-in-chief of one of the two flagship journals of the Control System Society, the IEEE Transactions and Control of Network Systems. Jeff, without further ado, I'd like you to take the stage.
Okay, thank you, Shrikant, for the invitation and the opportunity to participate in this colloquium. It's did I share the right screen or not yet? There we go.
Yeah, not yet. Yeah.
Not yet.
Yes.
There we are. All right, very good. And yes, I'm glad to be part of the colloquium, and I look forward to the interactions. And as Shrikant mentioned, yes, I will welcome questions throughout the talk. Okay, so the title of the talk is Feedback Control Perspectives on Learning. And first, I'd like to start with a couple of acknowledgements. And these acknowledgements are pointers to videos that you can find online. One of them is Automatic Controls, a Perspective by Carl Ostrom. And this particular video is from September of 2019. And the other video is called Respect the Unstable from Gunther Stein. And that's from way back in December of 1989. Again, both are excellent and highly recommended, and they've influenced today's slides. I also like to acknowledge a handful of folks who helped give valuable comments to put together the talk as well. All right, so the title of the talk is Feedback Control Perspectives on Learning. And so I'd like to first start with grounding my view of feedback control. And so if I had to give it my own definition, I would call it decision-making in dynamic and uncertain environments. we're interacting with a particular environment. We'd like this environment to behave in a certain way to realize a desired effect. And so what we do, we measure what the environment is doing, take a decision on what to do, and then act on that decision using our different ways to influence this environment. And so there's feedback control everywhere around us, and it's been applied in a whole variety of application domains: automotive, aerospace, manufacturing, energy, logistics, processes, communications, you name it. Feedback control has been applied. Two industries where it has had a lot of interaction is one is the automotive industry. And so here I'm showing a picture of a car, a vehicle, but actually there's many feedback control mechanisms in any individual vehicle. So we're probably all familiar with cruise control, and now it's adaptive cruise control, which will modulate the distance between your vehicle and the vehicle in front of you. But there's actually feedback control throughout a vehicle, controlling various aspects of suspension and engine and idling and braking and traction and what have you. Another industry where feedback control has played a major role is in the aerospace industry. And so here I have a picture of the X-29 aircraft. It was an experimental aircraft, and you'll notice that the wings are swept forward in this aircraft. And so here's a quote from the NASA website. The X-29 explored the use of computerized fly-by-wire flight control to maintain control of an otherwise unstable aircraft. The idea was that by having forward swept wings, that induces an instability in the aircraft, but that instability would also bring in higher maneuverability. What was meant by fly-by-wire is something we take for granted now, is that the pilot doesn't physically control the surfaces of the aircraft, but rather the pilot gives high-level commands to a computer, which then controls the surfaces of the aircraft to do flight control. And that's hence the terminology fly-by-wire. Also, a point to make here is that a human pilot cannot fly this aircraft. It had to, at the time, have been flown by computers. So when we talk about superhuman performance, at least for this kind of flight control, traditional controls approaches have had superhuman performance for decades. So I mentioned that controls is everywhere, and it's not talked about a lot. And so you'll find various synonyms, if you will, that indicate a feedback control loop of sense, decide, and actuate is present. So whether it's smart, active, autonomous, intelligent, self-guiding, self-regulating, self-adjusting, these are all ways that reflect that there is a feedback control loop that's active. And referencing Astrom's lecture, he mentions that it's easier to talk about devices than concepts. So it could be that feedback control enabled a particular application, but it's easier to talk about the robot or the vehicle or the rocket than it is to talk about the enabling concepts behind what made that device work. So feedback control is seldom mentioned explicitly, except when there's a failure. And so now here is a screenshot of a dashboard of a commercial vehicle, and it says motor control system failure. This might be the very first time the driver saw the words control system, and it's next to the word failure. So when it was working, control systems weren't mentioned, and then when it fails, then now control systems take the headline. And so this is a lighthearted illustration, but actually for safety critical systems, when control systems fail, there's costly and tragic consequences of these failures. And you can do this about any time in the year. Earlier today, I just did a web search with the keywords control system and crash. And this is what came up. So here's one headline: the reason behind pilot deaths. It mentions malfunctioning control system was blamed. Here's something regarding test driving of a Tesla, and it brings forward the autonomous vehicle control system's limitations. Here they weren't so much blaming the control system, but rather talking about testing outside of the capabilities of a control system, hence the control system's limitations. And that's something that we're going to talk about later on in the talk. But yeah, any time of the year, just put in the search control system and crash, and you'll get some pointers into what happens when control systems fail. So that's feedback control, this loop of sense, decide, and actuate. And now what's the relationship to learning? Well, in reinforcement learning, you have a learning agent that's also interacting with an environment. And through those interactions, the learning agent senses what's happening, does some adjustments to their decision process, and then actuates. That actuate may be for the sake of performance, might be for the sake of experimentation, but the point is that there's a feedback loop present in reinforcement learning. Also in multi-agent learning, so multi-agent learning, and we'll talk about this mostly during the talk, is learning in the presence of other learners. So the environment is actually other learning agents. While I'm trying to figure you out, you're trying to figure me out. And that again creates a feedback loop. And one thing that makes it different from the picture on the left in say in reinforcement learning is that the environment from the perspective of any single learning agent is actually a non-stationary environment. What do I mean by that? And the picture on the left, if I do an experiment yesterday and I do the same experiment today, then the outcome is going to be the same. There might be some statistical variations, but it's the same environment, and so I expect the same outcome. Whereas on the picture on the right, if I do an experiment yesterday and do the same experiment today, the outcome might be different. Why? Not because the experiment changed, but because the environment, the other learning agents have changed. They're in the process of learning and adjusting. And so this it's not so simple as taking a single agent learning approach and popping it into a multi-agent learning scenario because of this feature of non-stationary environments. So what's the value now that we see that we have feedback loops? The value of bringing in feedback control perspectives, we can use some tools on analyzing feedback systems. We can use some concepts on how to design, synthesize feedback systems. And then, as I mentioned, we also can understand not just what can be done, but also what cannot be done. What are the limitations of feedback systems? And I hope to touch on all of these. And so again, referencing Astrom's lecture on the benefits of feedback, he lists 3 benefits: stabilize and shape behavior, robustness to variations, and tracking command signals. And we're going to translate these benefits to 3 learning scenarios. We're going to talk about something called higher order learning, passive and monotone learning, and forecasting and no regret. And we'll elaborate on these one by one. And part of the discussion, we're going to use this running example in terms of longitudinal flight. And so I'll first show the video. And the task of this aircraft is a simplified flight control example. It just needs to follow the bouncing ball. And so that is the feedback loop. The ball's going up and down, and the aircraft is moving its control surfaces so that it can follow the trajectory altitude of this ball. What are the control surfaces that I just mentioned? The aircraft here in the back has what's called elevator angle. It is just going to move this surface up and down, and that will impact the trajectory of the aircraft. And we're looking at a very simple control architecture as well. There's desired altitude, which is the bouncing ball, the measured altitude, which is the actual altitude of the aircraft. That produces an error. The controller, that's the sense. The controller decides what to do and then acts on the environment by changing this angle. So we're going to use this example throughout to show the benefits of feedback and then how they apply to learning. And so the very first one is stabilize and shape behavior. And so let's show what happens if we don't use a controller to control altitude and just leave the elevator angle fixed, this control surface in the back, the tail angle fixed. What we're going to see is that there's some oscillations, and then eventually the aircraft drifts away. So without feedback, without actively measuring the altitude, it doesn't stay at a level altitude by itself. And so we need feedback to be able to maintain altitude. And so that's going to lead us to talking about multi-agent learning, and that will be the first context of stabilizing and shaping behavior. So we haven't started yet. We're about to talk about these 3 settings. I can take a brief pause here if there's any questions on feedback control before we migrate to feedback control perspectives on learning. So that's why we've just talked about feedback control.
If you have any questions, please post them on Q&A. Let me ask a question, Jeff. Maybe it's a clarification question for the audience, perhaps. So if you think of multi-agent learning, if you think of the vector of all the control actions of all the agents, then I guess you could just think of it as a single agent learning. So I guess what you're saying here is that you're interested in situations where each agent is making its decision based on some local information. Is that why it's different? So maybe.
And so actually we'll highlight that what makes multi-agent learning in particular different from single agent learning. But you're right in that, you know, it's based on local information. If somehow this information got disseminated to everyone, then it would look like a centralized setting. But also there's authority that we cannot dictate what the agents will do in terms of their learning algorithms as well. If it was centralized, then you can share information, and then you can specify how the different agents will update. And but now each agent is independent on how it can update its or do its learning at its own pace, its own style. So that's another distinction. Even if this information was shared, we don't have the authority to tell the agents what to do and how to learn.
Okay, thanks. And there's a question in the Q&A. Any thoughts? I guess two questions. The first one's from Daryl Farber. Any thoughts about why concepts are less discussed than devices? I guess that's referring to Carl Astrom's quote.
I was speaking for myself. That's not as cool. Okay, if you know, it doesn't have the same broad appeal. You know, how many videos? You know, how many times we watched the video of the Boston Dynamics robot doing a flip? But you know, we didn't really talk about all of the things, not just feedback control, but all of the things that went into that. That gets the headlines, as I said, until it fails.
And the second question is by William Sullivan. In your model, can humans be agents, or are they just control systems, or humans?
So actually, we're going to. I think it's important that they are humans, and back to Shrikant's comment is that okay. Even if we shared information, we cannot dictate how the agents will learn. If these were programmable devices, then we could dictate how the agents will learn and try to program. For example, if this was a multi-robot system, setting aside the issue of information, we can program them to learn in a certain way so that we can evoke a desired effect. And that's another field of say, a multi-agent learning where they're programmable devices. But we're going to take a lot of what we talk about is actually motivated by game theory, where the intent is to model human decision-making where we cannot dictate how the learning happens. And one thing that we'll get to in a couple of slides reflects that it's more of a model of humans rather than engineered devices.
Okay, so the next question is from Tin Doan. Can you elaborate more on the non-stationary environment in multi-agent systems? I guess he wants to know why it is non-stationary.
Okay, let me get to this through this set of examples and then come back to that question.
Okay, great, thank you.
Okay, so what's a multi-agent setting? So here's a simple setting of, say, fleet management. You operate 100 vehicles, there's a handful of routes, and you need to determine how many vehicles go on each route every day to get them from A to B. That's your only task. Get your vehicles from A to B with minimum congestion. The issue is that the congestion that your vehicles experience are a function of the decisions, the choices of other users of those routes. And so you have a coupling in these decisions. If there's another fleet manager, then they're also going to be deploying their vehicles on these routes. And the congestion that you experience depends on the routes you've selected and also the routes that others have selected. So that is a multi-agent setting. Another one is a common one that we may be familiar with and that kind of captures, although it's very, very simple, it captures a lot of what we're talking about. So in rock, paper, scissors, let's say that you don't decide rock, paper, or scissors, but rather you decide with what probability you're going to play rock, paper, or scissors. But the outcome depends on the probability of your opponent. And so you pick your probability, they pick their probabilities. And so the outcome doesn't depend just as a function of your own decision, but as a function of the decisions of others. These are multi-agent settings. And so now what does multi-agent learning look like? Well, let's look at single agent learning first. And here I have a representation of gradient descent. where I have a decision vector, and my new decision vector is my old decision vector plus some upward hill climbing. That depends on how I score my decision, my own utility function. So in standard gradient optimization, I just try to move uphill. And now here's the non-stationary environment. My gradient is not just a function of my own decision, but also of the decisions of others. And the decisions of others is also being updated according to a gradient hill climbing rule of someone else. And so now the gradient of one player depends on their own decision, but it also depends on the decision of someone else. And the decision of someone else is evolving on its own according to its own needs. And so from the perspective, you can compare these two, from the perspective of any single agent, their gradients, even if you don't change your decision vector, your gradient is changing. Why? Because someone else is changing. And so you can kind of visualize this in terms of a typical picture for gradient descent. Here, I want to walk uphill in this environment, but the landscape is changing. Why is the landscape changing? And it's because this landscape depends on the decisions of others. And so now what used to be uphill might not be as uphill anymore, or it actually might be downhill because others have changed. And that's the non-stationarity. So a learning rule, I showed gradient updating, but a learning rule pretty much, we're going to have this, this very generic representation of learning. My decision vector is updated according to the information that I have from the time we started, okay? That's a placeholder for a general learning rule. And then we want to ask questions such as, how does a learning rule behave with different environments? What learning rules are natural? And how do natural learning rules result in various solution concepts? One solution concept that you may have come across is that of Nash equilibrium. When would we stop learning is when we're all satisfied with our decision. And that's what a Nash equilibrium is, that my decision, given the decision of others, is what I would like to do. It's optimal with respect to the decisions of others. So these learning rules will eventually converge when they reach a Nash equilibrium. And we like to know when that happens or when it doesn't happen. And so here's an illustration of something very similar to reinforcement learning. It's called replicator dynamics. And what we have here is replicator dynamics, which is like reinforcement learning on rock, paper, scissors. This picture is showing the probability of rock, probability of papers, probability of scissors. And one agent is using replicator dynamics or reinforcement learning to learn whether they should play rock, paper, or scissors. But the issue is that the other player is also using reinforcement learning to play rock, paper, or scissors. If one of them was fixed with a strategy, a decision, then one agent would learn how to optimally play. But when you put these two together, they end up chasing each other. And in fact, it can exhibit chaotic behavior. So now we're coming to the concept of, say, modeling humans as decision makers. And one notion of learning that's natural, if you will, is what's been called uncoupled learning. And so in uncoupled learning, I can react to what you do, but I can't react to why you do it. You have some incentives, you have a reward function. I don't know what your reward function is. If these were programmable robots, programmable devices, we can inform each device what the reward function is of the other devices. But if it's a human with another human, then I don't know what why you do what you do, but I can observe what you do. So this is called uncoupled learning. And we saw that this one example of gradient updates is uncoupled. An agent uses their own utility function while observing what others are doing. But an agent never uses in their update rule the utility function explicitly of what other agents are doing. And a paper came out a couple of decades ago that said that if you have an uncoupled learning rule, then you cannot converge. These dynamics will never converge, and particularly they won't converge to a Nash equilibrium. And they used one environment, one game to illustrate that. So we have three players. Player one wants to be different from player two. Player two wants to be different from player three. Player three wants to be different from player one. And they're just picking left, right, or actually more precisely the probability of left and right. This does have a Nash equilibrium, but they showed that uncoupled learning rules, which have this natural interpretation, I can see what you do, but I don't know why you do it. They will never converge to Nash equilibrium for this three-player game. So now let's bring in a feedback control concept, and it's going to be stabilizing and shaping behaviors. So again, I'm going to show the aircraft following the bouncing ball. Remember, this tail angle reacts to the error in altitude, but actually it reacts into the error in altitude in a particularly kind of a little more sophisticated way than in a naive way. What if the angle was a function of only the current error? So what's happening here is the angle is a function of the current error, and it's unable to hold altitude. The way it's able to hold altitude before was that the angle was not just a function of the current error, it's a function of the history of the error, okay? But if you have the angle a function of the current error, then you can show that it will never be able to hold altitude. You have to use history to be able to hold altitude. So what we're going to do is we're going to use history in a very simple way. We're going to replace the gradients with an anticipated gradient. And how do we do this anticipation? This is just an illustration. If the gradient has a recent trend, I'm going to do a bit of an extrapolation and not move my gradients and function, not use my current gradient, but use the gradient where the gradient is trending. Okay, so we're going to replace the gradient with the trending gradient. And in fact, this will enable convergence. So you see it's still uncoupled. I'm not getting any extra information. I'm just using the information I have in a slightly more sophisticated way. And so when learning is unstable, the anticipatory learning can be stable. And in fact, it is stable for this game where it was concluded that uncoupling is, or uncoupled dynamics was an obstacle to converging to Nash equilibrium. Actually, it's not the uncoupling, it's because it was using its information in a uncoupled naive learning. But if you allow the use of memory, then you can get convergence to Nash equilibrium, even in this counterexample game. And there are other examples of, say, with replicator dynamics. I'm not really talking about replicator dynamics today, where you can turn chaos, the chaos picture that I showed you before, that chaos picture turns into convergence when you do anticipatory replicator dynamics, whatever that means. There are some connections to some ideas going on in optimization these days. There's always been kind of an interest in higher order methods using memory. And in particular, there's something that's called optimistic gradient descent. This is a lot to take in a flash, but pretty much what optimistic gradient descent does is it takes the current gradient and uses a difference in gradients to create an anticipated gradient. And so this idea is indeed built into optimistic gradient descent, which is getting some new attention in min-max learning for neural nets. Okay, so that's a natural breaking point. We talked about stabilizing and shaping behavior, and we can take any questions here.
I think you already answered the question about the non-stationary environment when you talked about gradient descent. So the next question, okay, I can interpret can AI ML applications be used for the multi-agent learning system? I guess maybe the question, let me rephrase it based on how I interpret the question, or you can interpret it any way you want, but I guess beyond just gradient descent, are there other AI ML applications that are sort of naturally blend into multi-agent learning systems? I mean, for example, sensing could use neural networks. There could be other aspects of AI that are used not just in the gradient descent part, but maybe for the sensing part and so on. How does it work when all of them are integrated into a multi-agent learning system?
Mm-hmm. So there, it's going to be, so there's one immediate connection is using two-agent learning for training neural nets, like in adversarial networks. And so that's kind of an offline training scenario. There can be now online scenarios where, say, you program a set of robots to do things like perimeter defense, or to do sensor, if you had mobile sensors, where the sensors should locate themselves. And sensor placement has that coupling. It has that effect that the value of putting a sensor at a particular location depends on where the other sensors are. And you can think about, say, deploying aerial vehicles to complement wireless coverage. And so again, putting a drone to help complement or support wireless coverage, its value depends on where you place it, and also where you place it is going to cause interference with other communications as well. And why do this in a learning approach? Because we don't know the environment beforehand. And so one approach would be to go out, figure out the environment, report it to a centralized node, compute an optimal deployment, and then send things out. Or you say, just let them figure it out through a combination of exploration and exploitation, figure out where to go based on the environment that's there, without doing reconnaissance first and then deployment. So I'm showing gradient descent, but the really gradient descent is a placeholder. Let's take, like, the key issue here was uncoupledness. Put as sophisticated of an algorithm that you want, it's either going to be coupled or uncoupled. Either the learning neural net or the simple gradient knows or doesn't know the incentives of other agents.
Right. Thank you. So I guess I noticed somebody raised their hands. We can't call upon people. So if you have a question, please put them in the Q&A. Thank you. Please go ahead, Jeff.
Okay, so we'll move on to benefit to feedback number 2, robustness to variations. So controls, feedback control is all about variations. It's obsessed with variations. And what do we mean by that? And so here we have a kind of in Flight Control 101, a set of equations that represent longitudinal flight. And what are some possible variations in these equations? Well, there's external environmental effects. Could be disturbances. It could be that when we measure the altitude, it's a noisy measurement of altitude. It could be that the atmosphere is changing, and then say that air density is changing, which impacts the various factors going into these equations. And it's helpful to distinguish 2 types of variations. There might be something that's parametric. For example, here I have thrust, drag, lift, mass, various aspects of the airframe. These might be uncertain quantities, but they're not introducing new states. The set of states is fixed. But there's other types of uncertainties, we can call them dynamic uncertainties, where you have to introduce new states. For example, say the airframe here might have been modeled as a rigid airframe, but actually it's a flexible airframe. I'm sure we've sat in the window seats and seen the window look like it's flapping. Okay, it's not a rigid aircraft. If you want to model that rigidity, then you have to introduce new states. Okay, so we'll call these dynamic uncertainty. How many new states? It could be arbitrarily or an infinity of new states that will be introduced. And so how can we analyze systems where we don't even specify the order or how many states there are? And so that is one of the things that is addressed in this literature of robust control. So in robust control, the questions go as follows. There's some system, or rather actually, so that let's back up a bit and talk about nominal analysis. Does my controller work for a particular system? Robust analysis, does my controller work for an entire family of systems where this family of systems might, it is characterized, it is, but it does not necessarily have a fixed number of states. There's more to it than a model with perturbed parameters. And so now we're going to move to using robust control ideas for learning, but first I want to make another connection. So what is the decision setup that we're using here? And because it's a simple decision setup that allows us to have this discussion, there's a set of channels like rock, paper, or scissors, or the different roads in commuting. Okay, there's a finite set of channels, and I need to allocate resources to these channels. Okay, it might be probability of rock, probability of paper, probability of scissors. That's going to be the resources that I allocate, or it might be how much of my fleet do I put on each of these roads. Finite sets, and I need to allocate, and there's going to be an outcome of that allocation. That outcome depends on the decisions of others. There's the coupling. Okay, so this is the setting that we're looking at. A finite set of channels, deploy your resources. What's going to happen depends on how others have deployed their resources. And so now, what does learning look like? When I deploy resources and everyone else deploys resources, that gets processed to give everyone rewards. Decisions based then impacts the rewards, which then impact the outcomes, and this cycle continues. So you see that that the learning is actually even more explicitly a feedback loop. And if you want to make a controls researcher smile, just show them a loop that looks like this. Okay, now we feel that we have a home field advantage where we can now bring our tools to this discussion. And so now what is robust learning analysis? Robust learning analysis will be, when does our learning rule work with a whole family of reward systems or games? I'm going to skip this where there's a connection to circuits that I'll just skip, and I'll talk about this setting as well. So if a learning rule has this property, okay, and what is this property? This property looks at the flow of resources and the flow of rewards. If the flow of resources and the flow of rewards are positively correlated in the long run, and if the environment, it's called a contractive game formally, but if the environment has that opposite effect, then if you put these two together, it will result in a stable learning system. And so a passive learning rule combined with an anti-passive environment, put them together, and they will be stable, and they will converge. They will converge in particular with a little more analysis to Nash equilibrium. And we haven't mentioned what is the order of the learning rule, if it's high order. Even we haven't mentioned what's the order of the game. It could be a high order game, but just put these two together and you have a learning scenario. Actually, our result is a bit stronger. If a learning rule has this kind of intuitive property that the flow of resources is aligned to the flow of payoffs, and if you want to stabilize all such games, all such environments, it has to be, actually this is a necessary condition, it has to be a passive learning rule, otherwise it can be destabilized. So now we're bringing in tools that allow us to talk about convergence without specifying the order of the learning rule or the order of the environment with which the agents are interacting. And that is another breaking point, so we can take any questions here.
So I'm curious about the comparison between MDP and POMDP. So are you saying that you could think of a POMDP as a perturbation of an MDP?
So that's what I'm saying, that any MDP, so if I want to, the comparison is that there's these neglected dynamics, such as the aircraft being rigid versus flexible. So then I think that in the continuous state terminology, I think I have the state, but I don't. So it's not actually Markovian in that short list of states. And similarly, if there may be parasitic dynamics, so it's not Markovian in the set of states that I've chosen to represent as states, there are kind of parasitic states that I haven't modeled that makes this violate my Markovian assumption.
That's a very interesting perspective, because I guess most of reinforcement learning assumes that there's an underlying MDP. What you're saying is that if you make sure that the controller circuit is robust, then it would also be able to handle if the states are, not what you think they are. I mean, there's some other hidden states. Okay, that's interesting.
So it would be interesting to look at things, even tabular Q learning, and just say what happens when I'm applying tabular Q learning when it's not Markovian in the set of states that I've assumed, where you'd have to now introduce what you mean by a perturbation, and is there a graceful degradation of performance?
That's a great viewpoint. There's one more question here. Natural systems tend to handle complex challenges in very smart ways. There's an emerging field of study called biomimetics. Do you see opportunities in learning from nature, and how?
I would say that even the anticipatory learning that is learning in nature. I said that we can't stabilize the aircraft with using the current error. We couldn't stand upright without using the history of say, our measurements of trying to stand. And so the learning algorithms that I've presented that use history are actually very, very intuitive ones, and can be found in nature, if you will.
Great, thanks.
Okay, so now we'll talk about tracking command signals, the third in Astrom's list of benefits. So here's the altitude. We want to follow the bouncing ball. And we can follow a bouncing ball when it's slow, but when the ball starts moving too quickly, we find that we get out of phase and we're unable to follow it. And so tracking a command signal has implicitly that this underlying command signal is slow and we can move faster than the command signal. Otherwise, we cannot track the command signal. And let's see how this can manifest itself or impact learning. So let's recall our decision setup. There's a set of channels, and I want to know how much resource to apply to each channel. Well, if somehow I was able to forecast what's going to be the payoff, yes, it's changing because others are changing. But if I could forecast what is going to be the payoff, then I can exploit that knowledge and assign my resources according to a forecasted outcome. So either I can try to forecast the consequences of my actions, or if I have the luxury of observing what others are doing, I can try to forecast what they're about to do and then pass that through and then know how to optimally allocate my resources based on forecasts. But this is a curious situation to try to forecast because remember we said with uncoupled learning, you don't have others' incentives. I might not have a model of what the others are doing. How do you do forecasting when you don't have a model? And actually there's a field for that of universal forecasting. And let me skip a couple of points here and talk about just this picture. So when the weather service forecasts rain, they don't say it is or isn't going to rain. They'll give a % chance of rain, 30% chance of rain tomorrow. How do you know the forecaster is doing a good job when they never commit to it will or won't rain? So one way to do that is to use what's called a calibration condition. And so let's take all of the days that a forecaster said 30% and keep a tally. And in the long run, what fraction of days did it actually rain? And if in the long run, it's around 30%, well, they did a good job. Well, not in general, they did a good job. They did a good job when they said 30. But let's test them again when they say 40%. Let's take all of the days when the forecaster said 40% chance of rain and do a tally, build this histogram. And if in the long run, 40% of those days it rained, they did a good job at 40%. And let's test them at a set of percentages, 10, 20, 30, 40. And if the weather service does a good job for all of these different tests, then we will say it is a good weather forecaster. It's a calibrated forecast. It turns out that you don't have to know anything about the weather to do calibrated forecasting. And there exist universal calibrated forecasting algorithms that whatever the sequence is, you're going to forecast percentages, likelihoods of outcomes, and you can always get it right, so to speak, using this calibration tools. Those calibration tools tend to be computationally and memory inefficient, but they're universal. And what we're going to do here is we're going to do a bit of a trade-off. And this is a very, very simple forecasting. And if you've seen recursive averaging before, it looks exactly like recursive averaging, except there's a fractional exponent here. Okay, to keep a running histogram with this exponent. And it turns out that this very simple forecast is not universal, but it works on subsets of processes. So again, I don't have a model, but what is the subset of processes? This forecast works on processes that move slower than my forecast. Remember, we talked about this timescale separation. If I can move faster, if my forecast can move faster than the process, then I can eventually figure out that process and do accurate forecasting. It's not universal, but that's what we're calling here. This is also calibrated, but it only works for slower processes and some fine print as well in other situations. So now I'm in a position, if my opponent is slower than I am, I can forecast what they're going to do. And here we see a handful of simulations that illustrate this kind of forecasting in what's called a no regret scenario. So you may have heard the term no regret. I won't elaborate, but remember we have a finite set of channels. One naive strategy is to use just one of our resources and never use anything else. Allocate everything to one channel. No regret means that our actual long run payoff is going to be better than had we just used one channel and stuck with it. Okay, and so here we see using two simple forecasting algorithms. But here we see I'm using a more sophisticated forecasting algorithm. I still have no regret, but actually my long run payoff is less. I can be too clever for my own good. Because this is a reactionary environment, when I was able to forecast them better, they actually changed their strategy. And now my long-term payoff is not as good as it used to be. In both cases, you have no regret. And if you've seen kind of more familiar with no regret algorithms, one of the points I'd like to mention here is that you can have regret for using a no regret algorithm in a reactive environment. One no regret algorithm might outperform another in a reactive environment, although both of them have no regret. And what enabled this was a timescale separation on being able to forecast my process, forecast my environment faster than my environment actually moves. Okay, and we can take a question here before I move to the closing segment.
So do you need to know something about the timescales involved to design the algorithms, or or is I guess like if you look at singular perturbation theory and control.
So that's what's happening here exactly. It's like, suppose you're using a running average and I'm using this running average that has that exponent, then over time, my step size will be arbitrarily larger than yours. So if you're using a vanilla no regret algorithm that does averaging, I'll do this kind of bigger time step averaging. And now you have exactly a singular perturbation applied to two time scale stochastic approximation. That's exactly the analysis.
Okay, thanks.
Okay, so we talked about these three benefits of feedback: stabilizing and shaping behavior. That led to higher order learning, and it let us better understand what is or isn't possible in multi-agent learning. Robustness to variations made a connection to passive or monotone learning, and that let us start to talk about the behavior of learning rules without imposing the robust behavior of learning rules without imposing the dimension of the underlying entities. And then tracking command signals has this built-in timescale separation, and that let us look at forecasting approaches to learning and understanding what happens when you have a timescale separation, but also leading, this is more of a question than an answer, to it says, can I regret using a no regret algorithm? So these are all things that controls can do. And before we get too excited, it's important to talk about the limitations of controls and what controls cannot do. And so here I'm going to talk about a waterbed effect. And what I'll illustrate here is, again, following the bouncing ball. There's a wind disturbance on this aircraft. And so it's able to follow the bouncing ball pretty well when the wind disturbance is at a specific frequency. But if I change the frequency of the wind disturbance, it cannot follow the bouncing ball. It cannot maintain altitude at all. Okay, so how come it does it at one frequency and not at another frequency? Well, the other question is that there's a built-in waterbed effect in that the better I reject disturbances at one frequency, the worse I'll reject disturbances at another frequency. You can't have it both ways. Okay, so good performance at one frequency will lead to worse performance at other frequencies. This is a so-called waterbed effect. And there are some features that make waterbed effects even worse. And one feature is when systems are called non-minimum phase. And I'm not giving the technical definition here, but I'll give an intuitive definition. Is that when, suppose I want to make the aircraft go up, then I have to lift the tail. But when you initially lift the tail, the first effect is that the aircraft goes down. For an aircraft to go up, it has to first go down. This is like a non-minimum phase behavior. If a system has a non-minimum phase behavior, then the waterbed effect, which was there, is actually even worse. So the better I do one frequency, the even worse I will do at other frequencies. So what causes the waterbed effect? Is it due to a kind of, a lack of sophistication in the controller? And so there's a lot of analysis that said if I have a linear system and use linear controllers, then you're going to have a waterbed effect. That was in the 50s. There was pioneering work in the 80s here in Illinois that generalized that to multivariable systems, and again established and quantified for multivariable systems this waterbed effect. And this is motivated by, say, a lack of ability to do computations, is to understand what are these trade-offs when it's limited on how sophisticated a controller I can use. But there's actually a nonlinear waterbed effect that was established in the 90s. And it says, even if you use a nonlinear controller, that you will have a waterbed effect. The only restriction on your nonlinear controller is that it can't tell the future. The action that it takes today is a function of the measurements that it's taken today and in the past. It's the action that it takes today cannot be a function of tomorrow's measurement. Okay, so if you have a causal controller, a temporally causal controller, so this, for example, could be as sophisticated as you want of a neural net, it cannot overcome the waterbed effect. If it does good disturbance rejection in one region, it will do poor disturbance rejection in another region. And to now reference Stein's lecture from 1989, he didn't call it the waterbed effect. At the time, he called it conservation of dirt. You can't get rid of dirt. You can move it from one place to another. And if you use good old-fashioned methods, this is what conservation of dirt looks like. If you use sophisticated methods, this is what conservation of dirt looks like. But you still have the dirt. You cannot get rid of it. And again, using very, very sophisticated learning controllers cannot bypass a waterbed effect. So this is something that controls cannot do, but it's something that any causal system cannot do. And okay, so that brings me to the concluding remarks. You're seeing a lot of interaction, and this colloquium has brought it, and there were some other colloquia that were being held through C3DTI that also brings together these communities of learning and controls. There's now a conference called Learning and Controls. There's a seminar series called Controls Meets Learning. You're seeing a commingling of keywords. You'll see papers that talk about no regret approaches to LQG. That's all kind of jargon, but the point is that jargon didn't mix 10 years ago, and now you're finding more mixing. What's bound to happen is a leveraging of success in each community, and I think it's a very exciting time to be watching these kinds of results unfold. You know, I did talk about what controls can do, what it can't do. This wasn't meant to be a presentation of tools, but rather it's a presentation of a perspective of how a control researcher might think about learning. And so it's inside the mind of a controls researcher. And so with that, thank you very much.
Thank you, Jeff. That was a wonderful talk. Some of you may know Jeff was invited to give a talk at the main machine learning conference in Europe. And I guess machine learning people are very, very interested in understanding what feedback control does and what control theorists have to say. And this is a wonderful perspective combining basic control theory and multi-agent control and so on. So if you have any other questions, okay, I guess this is this old previous question that's still here. I guess one question that I have is there's been a lot of interest in what is called multi-agent reinforcement learning. And I guess, I don't know if people are unaware of this or not, but people seem to assume at least some of the talks that I see or the papers that I see are trying to design controllers where different agents have different measurements. I mean, so there's a central system state X and I have Y1 and you have Y2 and somebody else. But we know from the basic Witzenhausen counter example that there is, solutions to this are just extremely difficult to find, even from a computational perspective. This famous paper by Tsitsiklis and Papadimitriou. So are people unaware of this? Are they just interested in just finding some local minimum using policy gradient and they're okay with that? Or what I haven't been able to get a proper answer to this question, and I was just curious what you thought of it as a control.
It depends on the people and who's aware of what, and also the angle that they're coming in. For example, let's take this issue of uncoupled dynamics. And so it was an obstacle. We were able to overcome that obstacle using memory. But the point is that an issue? Whether or not that's an issue, if you're modeling human decision-making, multi-agent human decision-making, it remains an issue. If it's engineered systems, then whether or not I know your utility function or the details of your utility function, It's other considerations. So, do we have the energy to communicate, to share that information? Are we in a communication denied environment? I have the energy, but not the channel. Is our environment too complicated? For example, what we talked about commuting, or this also happens, say, in routing and communications, that I can go from A to B and measure how much time it took. But I do not have a closed form expression of how much time will it take as a function of the cars and the time of day and the weather. I don't have this function. So it could be that I don't even know my own utility function. But the point is that it's different considerations. So now for multi-agent reinforcement learning, there's been a lot of work from the game theory perspective. There's been a lot of work in the CS perspective, along the lines of, if I take a single agent learning algorithm and plop it into a multi-agent setting, what can go right, what can go wrong? But if it's an engineered system, we can cheat. And then what's the penalty for cheating? It's engineering considerations. Again, communications, energy, stealth, complexity, and all, they all impact. But we're not taking it as a constraint. It doesn't have the same constraint as when it's human in the loop. So I think that there is a pretty good awareness, maybe not at depth, but when the more recent literature I've seen on multi-agent reinforcement learning seems to be taking the cheating approach and what's the cost of cheating.
Okay, I see. Okay, that's an interesting way to think about it. Instead of trying to understand when it is not possible, you can just say you can engineer things to make it possible, and how much does it cost? That's a good way to think about it. Okay, great.
So from the game theory perspective, it's brought up very differently, that you have something called Nash equilibrium, for example. It's an equilibrium where there's no dynamics, which is a very kind of curious way to talk about equilibrium. Usually you start with dynamics and then mention what's the equilibrium. So there, the motivation was plausibility arguments. What is a learning story for which Nash equilibrium emerges?
I see.
But it's not that Nash equilibrium is better or worse. It's just a
solution concept.
A backing to that solution concept.
Thank you. Is there a question in the Q&A? Can you elaborate on how MDPs/POM DPs are robustly handled with control?
So let me move to use the aircraft example. Okay, and so with the aircraft example, we say that there may be some parasitic dynamics, like the aircraft frame might be flexible and not rigid. Generally, that flexibility only manifests itself when there are certain excitations at a certain frequency. So if you take something and move it around slowly, it appears rigid. If you start moving it around very quickly, then it becomes its flexibility becomes apparent. So when you design the control system, you put in a self-limiter saying that I will not design my control system in a way that it shakes the system above, say, certain frequencies. Okay, and now there has been kind of efforts over the years to try to bring that kind of intuitive descriptions to POM DPs, but I think it hasn't been as clean of analysis, as clean of a setting. So it would be similar ideas that you want to say, I would like to be able to bound somehow the effect of all of these auxiliary states that I didn't model, but I would also like to understand what actions makes those auxiliary states start to act up, if you will. Okay, and with physical systems, they have intuitive notions of what actions I need to avoid to not excite these other kind of parasitic states. With POM DPs, it's less so. And there have been attempts over the years. Shrikant, what comes to mind for you of is there anything that's as clean as with
not that I know of, but I guess that's an interesting. I hadn't thought about it this way. You can think of just the probability distribution from states to observables themselves as part of the unmodeled dynamics, and try to see what one can say, whether one can say something about it. I don't think anybody has done that, but it's what you pointed out was an interesting way to think about it. At least points to a possible way to think about it. I don't know if anybody has done it yet, but it's interesting. Yeah. Well, I think we are at the top of the hour. Thank you very much. That was a great talk, and I will look forward to seeing you and others at next week's colloquium. Bye.